Okay. Well, it's good. Thank you for everybody for coming back. Hopefully, you're coming back because you enjoy my teaching and not because you're forced to, because I know you're required to take it to a class. But at least you gave me some decent. When you graded me, I came out okay. So it looks like some of you actually, may have feel that you've learned something useful from me. Unfortunately, I still can't make it to Israel, so I'm not sure when I'm going to get to Israel, but we'll see. Marina, what's the date of their graduation? When's their graduation ceremony?
I don't know yet.
When they said it, do me a favor and email it to me.
Of course.
Because we'll see when Israel allows me back into the country. Okay. So for the next 4 weeks, we're going to be doing something a little different than what we did last time. What we're going to be doing now is I'm going to be focusing on basically derailments and accidents and safety. And since the last time I covered a lot of the track derailments, track causes, this go round, I'm going to concentrate on the non-track ones, so you get a better idea of where the track fits in with the rest of the behavior of the railway system. So today, what we're going to do is I'm going to bore you to death with lots and lots of statistics, because we're going to talk about accident statistics across the board, both using a lot of European and British and American numbers, because I want to sort of get you an idea of where the safety problems are in the railway industry. And then after that, still today, we're going to talk a little bit about accident investigations. So a number of years ago, I gave a 2-day course on accident investigations to your safety department. So I'm not teaching you to be safety investigators from the point of view of I expect you to go out and do an immediate investigation. But I want you to understand what's going on. And I have a very interesting case study which we're going to give, which is going to be an accident that I investigated on Israel Railways a number of years ago, where I actually flew out and did the on-the-spot investigation. And it was a very interesting type of accident with very interesting engineering and safety and behavioral overtones that I think that serves as an interesting lesson. So we're going to cover that today as well. Next week, we're going to go into the mechanical side of the world. I'm going to talk about wheels, axles, bearings, and other mechanical types of derailments. And the process, we're going to get into the engineering behind it. So we'll talk a little bit about fatigue, and a little bit more about fatigue. I know we covered fatigue the last go around, but we're going to go a little bit more about fatigue and crack propagation and those types of engineering phenomena that you see. And you'll see that a lot of the problems associated with the mechanical side are cousins of the problems we see in the engineering side that we talked about last time. So again, there's a lot of interesting information there. The week after that, we're going to go into what we call human factors. We're going to go into those accidents caused by people and by mistakes people make. And we're going to talk about the relationship with things like positive train control and automatic train safety systems, the European train control systems, and how that is designed to reduce, but doesn't quite eliminate, all of the human factor type of problems and the operations type of problems. And then we'll get into some of the multiple cause type of derailments, which we'll talk about actually today. And then the last week, we're going to get into grade crossing accidents, which is a big deal in Israel. There's just a lot of grade crossing accidents in Israel. And we're going to get into, then we're going to go back into turnouts. So we'll go back into switches and turnouts, which are a big area, which we really didn't have a chance to cover the last time I taught you. So I'm going to give you a chance. So we're going to get a little bit into the engineering of switches and turnouts at the end of this class. So that's going to be the next 4 weeks where you have to listen to me. So as usual, if I want to give a break about every hour, 15 minutes or so. If I'm too caught up in my talking myself, feel free to interrupt me, around 10, 15, sorry, what time is it over there? It's 4 o'clock there. So let's say around 5:15 or so your time. We'll take our first break. Again, we'll take about 2 breaks in here. So let me share my screen, and we'll see if we can get things working here. As I recall, nobody likes yellow here. Oops, what happened? Okay. All right. So what we're going to do today is we're going to start off with lots of statistics, but I'm going to also talk a little bit about where a lot of this information is available. So a lot of the UIC has a database, and I have to tell you, I'm not impressed a lot by the UIC database because it really doesn't have a lot of what I'll call meat in it. But there's information there, and in a few moments I'll bounce back and forth and I'll show you what's out there. The information I'm going to present, although it's from the most recent report, which deals with 2020 accidents and previously, one of the problems I'm running into is this. One of the problems we run into, oh boy, live transcription. Somebody asked for live transcription, but that is giving me a little bit of problem. Not sure how I can disable it. All right, we'll leave it in there. We'll see what happens. Okay. I'll tell you now in the future, I'm not going to enable it because it's giving me a bit of a problem. I got too many things popping up on my screen. All right. All right. So I started to say the UIC data, the problem with 2020 data and even 2019 data is because of COVID, traffic has been down. And so be very wary of any reduction in accidents or safety, improvement in safety that you see associated with 2019 and 2020. Or 2020 and 2021, particularly. 2019 is probably okay, but 2020 and 2021 is that traffic was down significantly, and when traffic's down, of course, accidents are reduced as well. Okay, the UIC database that I'm presenting is a collection of accident reports from these countries. So you can see it includes most of Europe. In recent years, it's been expanded a couple of years ago. So among other things, it now includes places like Saudi Arabia, and the Ukraine and Turkey and even Iran data is in here, and South Korea data is in here. So again, one of the things you got to be a little bit careful about when you go back on UIC data is they keep changing the database. They keep adding countries to the database. And so it's, you got to be a little bit careful when you do year-to-year trends. Another source of data that I'm going to use. This is actually very interesting. A number of years ago, so this you can see, this is 2012. So this goes back a few years. The UIC instituted a study called the DERAIL study. And this is a study that looked at systems to reduce the occurrence and impact of derailments. And as a result, there was a major study of comparison of derailments and safety information from around the world. So in addition to the standard European data that was in here, Russian data was brought in there, American data was brought in there. I was actually a member of this committee. I actually was a member of this DERAIL committee. So I actually was the one who brought in a lot of the American data into the comparisons here. So again, you'll see data from this source as well. There's also a lot of good there's a lot of good British data. So in the British, there's the UK Rail Accident Investigation Board, and they have their reports. I'm going to show you in a couple of moments. And then we have the UK Rail Safety and Standards Board, the RSSSB, which has safety information, and then the UIC stuff. So let's see if I can figure out how to pull some of this up so I can sort of show you some of these standards. Let's see. Okay, so now let's see if I can figure out how to do that. Okay, can you all see the UIC safety database that I have up here?
Yes.
Yes.
Okay, good. All right. So this, and again, you saw I gave you the address for this one. This is the UIC safety database, online available. It's, I don't have access to the members only information, so I'm not sure what's in the members information. But if we come back, if we go down here, you'll see the UIC safety reports themselves. And so there's for example, I relied on the UIC 2020 safety database, which is this one report here. And you can see this is a 56-page report that shows a lot, that presents a lot of the safety statistics across the country, across the world, sorry. So I'll go through this in a little bit more detail, but this is an interesting source of information on UIC data, but it's not really what I would call a database. It's more along the lines of just a series of reports, and you can see it, there's an annual report over here. A more interesting database is this one. This is the UK, the British Rail Accident Investigation Branch reports. So this is an interesting set of safety reports. This actually allows you to search derailments by cause and rail type. So this is actually a very, very useful database. So for example, if I wanted to look at switch-related derailments, I would type in switch, and let's say I'm only interested in metros. I know we have a lot of metro people here as well as railroad people here, but you can see I do my search and it comes up with there are 4 reports over here. So for example, let's take the first report, derailment near Deptford Bridge Station. You can see this was in the Docklands Light Railway system. And so a accident occurred, this is 2008. And in this particular case, it calls it a switch derailment, but it really wasn't a switch derailment. There was somebody left a steel drilling rig on the track, and the vehicle hit the drilling jig, which is basically a structural element which is used to play. So it's a guiding jig for the drilling ones. So this was not quite a switch derailment. You got to be really careful. I think the derailment in Archway was a switch derailment. Let's see here. Yes, this is a more appropriate one. Okay, so here you can see this is Northern Line tube train. So again, this is London Underground Northern Line, and here was a broken switch rail. So there was a defect. There was a broken switch rail, and in the points leading to the reverse siding, and there was a defect in the surface of the back on the surface of the rail at the back end. So there were a bunch of problems that combined, which you'll see. There were three contributing factors: the broken switch rail, the defect in the surface, and a lack of a chamfer in the edge. So a fatigue crack. So what happened is the defect basically grew from fatigue, broke the switch rail, and that caused the derailment. And if you really want to if this is something that's of real interest, you have the ability of actually downloading the full derailment report and seeing the entire accident report, which I'm not going to go through. This is just really to familiarize you with this kind of information. So, for example, if you were interested in heavy rail instead of light rail, you can see the derailment in Grey Rig we'll actually talk about in detail. That was a very nasty switch type of derailment on British Rail and Network Rail in a place called Grey Rig. So again, this particular website is one of the more useful websites I find for looking at accident information. We also have the U.S. Federal Rail. Oops. Let's see what happened here. Okay, so we also have the U.S. Department of Transportation Federal Railroad information under railroad safety. There's an entire database that's accessible. And again, I'm just going to show it to you right now very briefly. Again, we'll go through it a little bit later, show you where it is. But you can start searching for gross accident trends, or you can actually go in and look at individual accidents on a specific search basis. Okay, so let's go back to my PowerPoint presentation. What just happened here? All right, for some reason I can't get my highlighter back up again. Oh. Hold on, I'm gonna come back here. Oh, there I am. Okay. Can everybody now? Can everybody see the slide that says source of U.S. accidents and derailment data?
Yes, we see.
Okay, good. So I just showed you where the FRA safety database is. There's another database which I can show you called the NTSB, National Transportation Safety Board, that have the very specific accident investigation reports, which tend to be about 100 to 200 page reports in very great technical detail about the accident, what caused behind it. And then Canada has a very similar database, which I actually like because it has a very good search feature, very much like the British system. So again, these are all going to be useful databases if you're going to be at some point looking at needing to get information about these kinds of safety behavior. All right. Okay, now one of the other things you got to be careful about when you're comparing accidents from different sources is the damage reporting threshold. So, for example, the U.S. database reports any accidents that has then more than $12,000 worth of damage. So, which is not a lot of damage. So there are a lot of very small accidents reported in the U.S. database. Accidents of the order of about $12,000, $15,000, $20,000 worth of damage. Let's say 10, 12, 15,000 euros. The UIC damage threshold, on the other hand, is 150,000 euros. So it's more than 10 times the threshold for the US reporting ones. So as a result, you're going to see a disparity in numbers. You're going to see a lot more accidents coming out of the US system than out of the UIC system. And we see the same thing when we look at Russian data. The Russians also set a very high threshold. So the threshold for accident reporting is high on the Russian data as well. Okay, so let's talk a little bit about rail fatalities. Basically, in the UIC, and by the way, we see the same information behavior in the US, and we see a lot of the same behavior around the world. Really, less than 1% of all railway fatalities are passengers. When we compare fatality rates on rail to fatality rates, for example, on a highway, railways are much more safer. And it's even more so in Israel, and where the highway fatality rate, unfortunately, is very high. But generally, less than 1% of all reported rail fatalities are passengers. About another 2% were staff. So basically, passengers and staff make up only about 3% of all reported railway fatalities. So the obvious question becomes, where are the rest? Where are the other 97%? And they come mainly from these two sources. They come from trespassers, which is basically somebody who's either on the railroad track or on the railroad who has no right to be there. This is usually people walking along the track who obviously you're not supposed to be walking along the track, but trespassers represent actually the largest single category of fatalities in the world. Across all systems. The other major category of fatalities are level crossing users, or people in automobiles or trucks that are hit by a rail vehicle. And in 3 weeks, on January 25th, I'm going to have an entire hour plus part of our lecture devoted to talking about level crossings and what can be done to prevent it. What are the problems? It's a major issue. You can see down here from this graph. Again, you can see the division fatalities are around 0.6. The 0.6% are passengers, the 2.6% are staff, and the remaining 97% are the trespassers and level crossing users. If we look at injuries, the distribution is a little bit the same, a little bit more passenger and staff, so they represent roughly about 7% as opposed to 3% of injuries. But again, 92% of all serious injuries were trespassers and level crossing users. So again, this is, and again, although these numbers are UIC numbers, the exact same type of behavior we see everywhere in the world. Okay, so if we look at accident trends, now again, you got to be, again, I caution that we got to use 2020 numbers with a grain of salt. And if we just look at the red column here, you can see that there's actually been a reduction in the number of significant accidents associated with the UIC rail, the UIC railways in the last 5 years. And that is due to the fact that there's been a lot of effort put by rail systems in the last couple of years in controlling accidents, and also with the implementation of positive train control and European train control systems. The automated control safety systems are actually working, and we're actually seeing reduction in those classes of derailments associated with operational type of controls. And we'll talk about that as well. So again, if we look at the number of significant accidents, and a significant accident is basically where you have a person, either an injury or a death or significant damage, which in the UIC world is north of 100,000 euros. And again, you can see these 4 years here. If we look at significant accidents and let's look at the established members, just because we don't have data going back for the new members. You can see that from 2015 to 2018, the numbers are more or less the same. There's no significant decrease up until we came to 2019. 2020, again, is an anomaly because it's a COVID year, and traffic was significantly down. So it's hard to make a judgment on here. Okay.
Sorry, Alan, what is new members? I don't understand any.
So, okay, I glossed over that. So let me come back here.
Okay, I understand. This is a new Ukraine and things like this. Okay.
Yes, exactly. So, so one of the problems I find with the UIC database is it's a bit of a moving target. That's why I'm just showing the established members. You can see this new member data doesn't start till 2018. So in a couple of years, if they don't add new members, this is going to be interesting. But this represents about 30 odd railroads right in here. Many of them Western and Central European railways for the majority. So you actually have a lot of rail systems that are comparable to Israel. And if you want to start look at the smaller European countries, if you start looking at places like Portugal and Netherlands and places like that, the volume of rail traffic is probably not grossly out of line with what you see in Israel. Okay, so again, when you look at the accidents by type, 78% is an individual hit by a train. Collisions and derailments, again, represents a relatively small percentage of the total number of accidents. This varies a little bit. In the US, it goes up to about 10% because of the lower damage threshold. So roughly 10% of all accidents are associated with derailments or collisions, and then 90% are associated with either grade crossings, level crossing. You can see in this particular case, shunting operations is also really a rail operation. So you got 4, 7, about 8% of all these accidents.
What is shunting operations?
Shunting is when you're moving a rail vehicle in a yard. So if you have either a freight wagon or you have a passenger coach in a yard, and you're moving it around. For example, if you're making up a train in a yard, and you're moving individual wagons from one track to another, that's called shunting.
Okay.
And you'll find that there's a very significant number of accidents that happen in shunting operations for a variety of reasons, not the least of which is that you know from experience that yards are not as well maintained as mainline track. So track condition is not as good in the yard. So we see a much higher percentage of accidents and particularly derailments in yards. Okay, so if we start looking at the major causes of accidents, again, this is UIC data. Again, what we call third parties, which are trespassing, level crossing, etc. 88% of all reported accidents are associated with trespassers, which is the big one, level crossings, pedestrians, etc. Then 10%, so this goes back to what I was saying before. So about 10% of all accidents are really associated with are really collisions, derailments, are real what we call railroad accidents. And 90% are accidents when we're hitting a trespasser, or we're hitting a vehicle at a level crossing. And by the way, it doesn't have to be the train hitting the vehicle at the level crossing. If a vehicle runs into the side of a train in a level crossing, that's also considered a level crossing accident as well. And unfortunately, we see a bunch of those as well. We're going to go into this in more detail, but you can see that infrastructure, rolling stock, and human factors are going to be the three major causes of accidents, of railroad derailments and train accidents. And so we're going to spend a lot of time talking about those. And in fact, we're going to spend an entire lecture on rolling stock accidents and another lecture on human factor and operations accidents. Okay, again, I'm not going to go through, anybody who really is interested in getting more information on that, this is all right out of that UIC report that I showed you earlier on the UIC website. The address I gave you in one of the earlier slides, so you have access. You have the internet access, the internet address, sorry, so that you should be able to find it and look at that. So again, if we look at the trends, and let's cut off 2022. These, it looked like we came up in 2016, and then from 2016, there seems to be a decrease here. In general, if we look at safety over an extended period of time, 10 years, 20 years, 50 years, you'll see that for the most part, the trends are downward. But one of the problems we run into, and one of the problems we find, is that the trend down for train derailments and train collisions and train type of accidents are down, but the trend for level crossing and trespassers aren't decreasing that dramatically. In fact, there doesn't seem to be any real recent decline in that. And this is one of the problems that really face the railroads around the world. And again, we'll talk about that in more detail in a different lecture. The good news, unfortunately, what's happening is this. These words that are coming down in the bottom of it interfere with my vision, so I have trouble seeing it. This actually looks at the breakdown between accidents between stations and on open lines. And again, you can see that there are a significant lot of accidents at stations. Again, this is UIC type of data. If we discard 2020 and focus on 2015 to 2019, about half the accidents are in open line, about 30% are in stations, about 20% are in level crossings. By the way, these include trespassers. We see trespassers accidents at stations. We see trespasser accidents at open lines.
Alan, level crossing, you mean on junctions?
Oh, sorry. I thought everybody's familiar with that term. Level crossing is what in the United States we call a road rail crossing or a rail crossing. It's where a road crosses the railroad track.
A junction.
I'm hesitant. Is that what you call it in Israel? Because junctions means different things in different parts of the railroad world. So I don't like the term junction, because a junction in railroad terminology can sometimes mean a place where two tracks come together.
I see. Thank you.
So I don't usually use the term junction. The most commonly used curve terms in the world are either level crossing or road rail crossings. So basically where some sort of road goes across the railroad track at the same level. In other words, we're not talking about where the track and the road are separated. We're talking about where the road and the railroad or anything go across each other. So there's a potential for an automobile to be hit by a train or a train automobile to hit a train. Again, if we look at the victims of railway accidents, again, you can see that for certainly from 2015 to 2018, there's no downward trend. 2019 had a good year. 2020, really not excited about because the numbers are COVID related. Now, what becomes really interesting is, so we're talking about numbers of accidents here. You can see we're talking about number of accidents in the thousands. Now let's talk about train accidents, where the accidents are only the train. And like I said, that represents about 10% of the total, roughly. So you can see here that the number of derailments that are, and again, this is UIC data, is of the order of 100 a year, 110 a year. You can see it varies a little bit. And again, there's no clear downward trend. Here, by the way, you notice 2019 is higher than 2018. And again, in the UIC data, the data is roughly 60-40 open line versus station. By the way, you notice 2020 still had a significant number of derailments. If you look at the United States, for example, first of all, notice that the total number of accidents is of the order, again, 2020 and 2021 are COVID years, so we won't look at that. But you can see the total number of accidents are of the order of about 12,000, of which about 1,000 or 1,100 are train derailments and collisions, and the rest are level crossings and trespasser incidences, with the total number of fatalities hovering at about 800 a year. Again, 97% of those are trespassers or level crossing users. So one of the obvious questions here, which I'll answer before somebody asks it, is how come there are so many more American accidents than there are European accidents? Two reasons. Number one is the reporting threshold. The reporting threshold for an accident, what's called an accident in the United States, is anything greater than about, let's say, 11,000 euros, whereas an accident in the UIC is about 120,000 euros. So there's a factor of 10 difference in the reporting threshold. The other thing is traffic density. Believe it or not, the traffic density in the United States is almost 10 times the traffic density of Europe. If you look at the total number of ton miles operated in the United States, you get the same in Europe. When I first joined the derail committee that I reported earlier, I was getting a lot of grief from the European railroads telling me how come the Americans have so many more accidents. But when we ended up normalizing the accidents by amount of traffic, it turned out that the US derailment rate was not all that different than places like the UK and France, because of the much higher traffic range. So again here, I deliberately picked pre-COVID numbers here because I didn't want the COVID numbers in here. So if you look at the US, you can see there are about 12,000 total accidents or incidences, but of those, total train accidents are less than 2,000. Highway rail crossing incidences are another 2,000, and trespasser incidences are close to 8,000. So the bulk, this is very much consistent with the UIC data that I showed you, which basically says that this is a worldwide phenomena. We see this all over the world, that trespassers, people out on the track, represent a disproportionate number of accidents of the order of 70% or 70 to 80%, depending on where we are, but roughly around 70%. You know, so if you take a place like Japan, for example, which probably has one of the world's best railroad safety records. For example, the Shinkansen, the high-speed bullet train of the Japanese railways, never had a derailment in its history. Just hasn't had a derailment. It's a phenomenal safety record. But in Japan, one of the favorite methods of suicide is to jump in front of a train. And so the Japanese railways have a really nasty trespasser rate. So again, this is US data, but you can see it's not inconsistent with what we saw elsewhere. Total train accidents, about 15%, highway level crossings, about 20%, and about 70% trespassers and others. Again, if you look at a 10-year trend, this is accident rate. So this is the number of accidents per million miles of railroad operation. This is US data. You can see that over the last 10 years, there's been no real, there's been a period where it went down, then it came up. It turns out that actually these were 2 years where traffic was down a little bit, but this is normalized. So this should be independent of traffic rate. Collisions. Now here it's very interesting. You can see it was very level for a while here. And then all of a sudden it dropped significantly in 2016. This is where positive train control was introduced, where we introduce the next level of train control systems, where the trains can be braked automatically by the control systems if they are going over speed, or if there's a collision, or if there's another train on the same track. And you can see it hasn't eliminated it, but it cut it in half. Derailments, again, you can see are more or less, there was a slight drop over here, but maybe from 1400 to 1250, but certainly not a spectacular drop. Now this is a graph that takes a little bit broader perspective. So this starts at 1975. So this is about a 45 year time horizon we're looking at here, from 1975, and let's stop right about over there, which is the pre-COVID era. So total fatalities are in red. You can see that has a very distinct downward trend. Total injuries has a very dramatic downward trend. Employee on duty fatalities. This is particularly interesting. So this is railroad workers. Employee on duty refers to a railroad worker who's working, be it a track worker. For example, for many years, track workers were the biggest cause here, because you would have people working on the track getting hit by a train. This is a real problem across the board. Washington Metro, for example, has had a number of employee fatalities over the last couple of years where track workers were hit by train. And there's a whole series of technology that's been developed over the last decade to try to address that. We'll talk about that also in a later class. But what you can see is employee on duty fatalities were in the 100 to 120 range in the 70s and going into the early 80s. And now they're in the range of 10 or even less, 5. We in the last few years, employee on duty fatalities are generally less than 10 across the entire United States. Here again, you can see the kind of casualty data we're talking about. We got highway, rail, and trespassing incidents account for 99% of all fatalities in the United States. It was 97% in the UIC. So in 2019, which is the last pre-COVID year, there were 860 fatalities total, of which 9 were employees. I think there were about 2 or 3 passengers, and then the rest are either trespassers or level crossings, with trespassing being the largest number. If we look at the distribution of train accidents by track type, we see that main track represents about a third of all the accidents, and the rest are yards, sidings, and industrial track. If we look at the accidents by collision versus derailment, you can see that collisions represent a very small percentage. And this is going down again because of positive train control. What's really interesting, again, is that 60%, 50 to 60% of all accidents are in yards. The United States, only 4% of all accidents involve passenger trains, but that's deceiving because passenger trains represent about maybe 5% of all the 5 to 6% of all the trains in the United States. So we got to take that number with a grain of salt. And again, derailments, collisions, others. Okay, so now let's look around the world by country. So this represents freight railroad derailment. So for the period 2005 to 2010, normalized with respect to volume of traffic. And you can see I'm comparing US, Russia, France, Austria, the UK, Germany, and UIC in general. So the first thing to know, so we look at the number of derailments per billion ton kilometers. You can see the Russian data was very questionable. This was data was provided by the Russian railroads to the UIC derail committee, and we didn't believe it in the beginning. So I'm gonna put a big question mark next to Russia. But if you look at the derailments, again, this is per billion ton kilometers. Does everybody remember what a ton kilometer is? So let me refresh the memory. So a ton kilometer is moving 1 ton of good, 1 ton, 1 kilometer. So to put it in perspective, if I had a 1,000 ton train, going 100 kilometers, that would give me 100,000 ton kilometers. So you can see this particular unit is normalized by billion ton kilometers. So a billion ton kilometers would be 10,000 of these 100-ton trains going 100 kilometer. So you can see the United States derailment rate's about 0.75. The British derailment rate's about 0.96. The German derailment rate's about 0.12. The Austrian's about 0.25. If you look at the derailment cost per billion ton kilometers, you're looking at about 75,000 euros in the US, 90,000 euros in France, 156,000 euros in Austria, 162,000 euros in UK, and 93,000 euros in Germany. So the average cost per reported derailment, the average cost per derailment per billion ton kilometers you can see is about 6 euros in the US and about 600 euros in the UK. Again, looking at the number of derailments. So this is derailments only. The US has about 11,000. The UK has 257. The UIC in total has 403. Total cost of derailments, about $1 billion in the US. $60 million, a billion euros, sorry, 60 million euros in Germany, 40 million in the UK. The average cost per derailment. So why do we care? Why am I even bothering looking at all these numbers? Well, one of the things you can see from the average cost of derailment is giving you an idea of the severity of the derailment. A derailment that does 100,000 euros worth of damage is significantly less in scope and volume than a derailment that does $700,000 in damage. So again, we can see the effect of the different derailment thresholds very clearly here. Volume of freight transport in billion gross tons. So you're looking at 14 trillion ton kilometers in the US, as opposed to about 2 trillion in the UIC total. And again, these are the same numbers I showed you before, derailments per billion ton kilometers. All right. I want to take a break here because by now everybody's totally bored looking at the numbers. Hold on a second. Let me see. Because what I want to do next is I want to break down these numbers between the different types of causes. I want to get a little bit more into the engineering of the issues and start talking about the different causes of derailments. Because one of the things we're going to get to, and I'm going to be talking about an Israeli railway derailment that occurred about, I'm going to say about 10 years ago, if memory serves me right, in a place called Kfar Menachem. That's going to be a good, in addition to be a really interesting case study, it's going to be a good example of why do we care? Why am I bothering you with all these statistics? You guys are sort of just, you just want to design your railroad and off you go. And the point I want to make is when you understand where the causes of the derailments are, you can figure out better ways on how to improve the safety of the railway, either through design, through inspection technologies. And by the way, one of the things I'm going to be covering over the next several weeks is I'm going to also talk a little bit about what inspection technologies are being developed and what's out there to help prevent the kinds of problems we're talking about. And again, the Kfar Menachem derailment was a really interesting derailment. I'm sort of leaving that for the end of today's lecture. But the Kfar Menachem derailment, and this is why I'm trying to keep you interested in this. The Kfar Menachem derailment dealt with the issue of, okay, I have the cause of derailment. Do I have that same cause prevalent elsewhere? It turned out the Kfar Menachem derailment was associated with this particular type of wagon. And when they went out and they actually inspected the wagons afterwards, what they found was that just about every wagon in the Israeli railway fleet had the same problem. It just hadn't progressed to the point where it was going to cause the derailments. And as a result, this whole population of wagons were pulled out of service, and a major fix was developed and implemented before those wagons were allowed to come back into service. And it's a really good example of why you do a detailed accident investigation, why you study accident statistics from an engineering point of view, so that you don't run into that problem again. For those of you who are in the metros, one of the problems we run into all the time that fall into that category is the fact that we see one set of standards used in the design of the vehicle and another set of standards used in the design of the track, and the people don't sort of put it together. They don't talk each to other. The vehicle designers are off designing the vehicle. The track people are off designing the track. And then all of a sudden they put them together and they find in the first week of operation or the first couple of weeks of operation, I have all these derailments, usually low speed, fortunately, usually small. But I've seen this in a half dozen metros now, both light rail and heavy rail, where the first week, I remember when I was a consultant in this world and I was doing derailment studies. I go to the metros, the people, the teams that are putting together the metros, and they'd say, oh, we have expertise, or we have vehicle experts, we have track experts. We don't need you to talk to us about interaction. We understand interaction. And then I get a phone call the first week of operation saying I got a vehicle that went on the ground. What happened? And I go out there, and it was a lack of understanding of the interaction between the vehicle and track. The causes are really critical in defining this. So again, forgive me for boring you a little bit with numbers. And I promise you it's only going to be for the first half of this class. And after that, we're going to go really into the hard engineering of it. But I want you to understand where these numbers are coming from. Okay, let's take a 15-minute break. I got 5 after, so let's resume at 20 after, and then we'll go from there. On the 25th, we'll talk about that. But in the meantime, now I want to focus on the railroad-related accidents and start getting us into the point where we start understanding the different types of accidents, the mechanisms, the engineering behind it, and ultimately allow us to learn how to avoid those kind of accidents in the future. And particularly through improved engineering, design, inspection, and maintenance. So if we look at the major causes of train accidents per se, We typically divide them into three parts in a manner similar to the way we divide the railroad itself into three parts. If you recall from my lectures way back in the beginning when we had them last time, we talked about the fact that there are usually three groups within the railroads: the equipment department, the infrastructure department, and the operating department. Well, we divide accidents exactly the same way. We divide accidents into the equipment group, vehicles, which includes locomotives, wagons, passenger wagons, freight wagons. Sometimes you'll hear the term called rolling stock is a term that's commonly used in the railway industry to refer to the vehicle part of the industry. And again, that's one of the major cause areas, not only in the UIC, but in virtually everybody, and all the categorizations. Infrastructure, which is really where most of everybody in this group belongs. Everybody here is pretty much associated with infrastructure. It's interesting, about a month and a half ago, the Technion started another lecture for the rolling stock people, and I gave the first 4 or 5 lectures for that one as well. So now I'm getting to address all sides of it. But the infrastructure includes the track, the traction power, third rail, overhead catenary, power generation substations, signaling systems, bridges, buildings, stations. That's all falls under the category of infrastructure. And then the third category is operations, which includes the movement of trains. Under operations, we have a subcategory called human factors, which are usually has associated with drivers and people on the ground doing something that would affect the operation of the train, such as somebody manually throwing a switch. That would be either operations or human factors. Loading of wagons, for example, overloading of wagons, improper loading of wagons, that tends to fall under the category of operations as opposed to vehicles. So very often there's a sort of a fine line defining the three different zones. Okay, if we look at the UIC data, what we see is that it's roughly a third, track or infrastructure and rolling stock are both represent about 37% of the total. So this is my infrastructure over here. This is my rolling stock over here. Operations are only 25%. And then there's miscellaneous other, so for example, extreme weather. If there was a hurricane blowing and it blew train off the track, that would be an other category, usually associated with environmental weather. So what's interesting, and you'll see this come up later on, in the UIC breakdown, operations and human factors represent about 25%. So they're significantly less than infrastructure and rolling stock. When we go to the US data, which I'll show you in a few moments, what we find is that the operations and human factors are larger than the infrastructure and the rolling stock. And part of that has to do with the threshold. Again, what's reported as an accident? In the US, there are a lot of very small yard type of accidents where the damage is maybe $15,000, $20,000, $25,000 total damage, equipment and track and everything, which is not a lot of damage. You destroy one vehicle. If it's a passenger vehicle, it's probably $1 million right there. It doesn't take much generally to do $25,000 worth of damage. But do you remember the UIC threshold is about 120,000 euros? or about $150,000. So virtually every one of those small accidents gets cut off in the UIC database. And so these operational accidents are only very large accidents, collisions, for example, where a lot of damage is done. Again, looking at it by year, okay. The green represents human factors. The purple represents users, which is really an operations one. So really the operations category that I show over here includes both of these categories as well. Then you can see the rolling stock and the infrastructure. If we look at it by, again, if you look at the UIC data, you see, you notice by now the numbers change a little bit depending on which study we're reporting at. This particular data comes from a European study called the DNV study, which was a separate independent study of accidents by of only European accidents. The UIC data is slightly different. Here, the operations and human factors are a little bit more significant. RSSB is British data. So the British data is similar to the US data, where the operations and human factors are the largest category, infrastructure is the second largest category, and then rolling stock and other, and there's always an other that gets involved in here. Again, looking at a longer term trend, and again, let's get rid of the COVID era data. So here you can see human factors are dominant category. Equipment, signal. This is actually US data that I'm looking at right over here. So the US data, as I indicated, human factors are the largest category, and that difference from the UIC, again, because of the reporting threshold. Track, miscellaneous, which includes weather and third-party operators and things of those sorts. Equipment. And then the US also has a separate category for signals. And you can see signal-caused accidents are far and away the smallest category. Signals are not a major category. In fact, the UIC doesn't really split it out separately. If I look at main track accidents, though, okay, so let's walk away from the everything, including the small accidents, and look at main track accidents. And what we see in the US is that suddenly track is the far and away the largest category of main track derailments. So that brings us back to the group that you're representing, which is the track people. And we'll talk about where they come from in a few minutes. We'll dig deeper into it. You can see signals a blip, like 1 or 2. Signals just are not a main cause of main track derailments. Human factors, which were dominant, human factors which were dominant over here, you can see are sort of number 3 on mainline tracks. So that's consistent with the UIC data that I showed you over here, where again, if you deal with main track derailments, you get rid of a lot of the smaller derailments, and they're more expensive, bigger derailments. And so again, this is sort of track is number 1, equipment's number 2, human factor is number 3, miscellaneous is number 4, and signals are sort of a distant 5. If I look at costs, typically costs can be broken up into 3 categories: track damage, wagon damage, and disruption damage. Now, this is the UIC reports their accidents to include track damage, wagon damage, and disruption damage. The US data that I'm going to show you only account for track and equipment damage. So the average cost of a freight derailment in the UIC is about €1 million. And is a major cost associated with operating disruptions. What do I mean by operating disruptions? The track's out of service. You can't run your trains. You have to reroute the trains, often at the cost of a lot of distance. And in the case of Israel, you may not always be able to reroute the trains because you don't always have multiple routes. If both tracks are blocked in a derailment, then you may be stuck and you can't run anything until you clean up that derailment. So again, the big 3, infrastructure, rolling stock, and human factors, and then the others, weather, and the UIC signaling are in here, third party operations. And again, I'm not going to go into this. You can see it differs a little bit by country, which is very interesting. These are only European countries. So, for example, the yellow or the orange is Germany. The purple, the light purple is Great Britain. This dark blue is France. The red is Austria. The black is UIC in general. The green is this DNV study, which is a study of combined European railroad activities. So, for example, remember we said Britain was showing similar behavior to the US, where operations were the number 1, infrastructure was number 2, and rolling stock was number 3. Germany, on the other hand, follows Germany has rolling stock and operations tied for number 1, and infrastructure is a number 3. So again, interesting to look at the comparisons here. If we look at different parts of the world, the US is in green, Russia is in red. DNV represents, again, a set of combined European ones. UIC, again, is this purple. This is the breakdown of infrastructure itself, by the way. So we break down infrastructure here into 4 major categories: structural failure of the track superstructure, rail and sleepers and fasteners, for example. Track geometry failure, twist, alignment, surface, profile, failed substructure, and other. So you can see that for the most part, track geometry failure seems to be the largest breakdown of infrastructure, followed pretty closely by breakdown of the superstructure. Substructure is a very, very, very low percentage of total failures, and then the broad other category. So again, this is the ENV, the European Union DNV studies. This is an EU study. Track geometry is number 1. Superstructure is number 2. Substructure is number 3. If you look at the US data, you'll see track geometry and rail are almost the same, with frogs and switches and turnouts sort of number 3. Roadbed, which is substructure, is a distance 4, and other. You go down a little bit further into the process, and so this is a comparison of US and DNV and Russia. So you can see, for example, the US has far and away the largest amount of rail failures. Why? Because they had the axle loads. Remember, US axle loads are 33-ton axle loads as opposed to 27-ton axle loads or 25-ton axle loads for the UIC countries. Israel is a 25-ton axle load. If we look at the geometry categories here, you'll see that this is where you'll see the European data coming out. Excessive tracks, twist, cant, track width. So again, the geometry takes the dominant case. Again, this is a comparison of European studies. It varies depending on country. One of the interesting things is if you start looking at the top 5 or 6 categories of infrastructure failures around the world, they're very similar. Here are the top 5 European infrastructure categories: excessive track width, excessive track height, and excessive track twist. So these 3 are geometry. Rail failure is number 3. Track superstructure unsupported by substructure. So that means a poor tie, sleepers, ballast, or something like that. And switch component is number 6. If we look at the rolling stock, and again, we'll talk about this next week. We got wheel set failure is number 1. And that we seem to see throughout the world. Throughout the world, we seem to see wheels are the number 1 cause of failure. Well, it's not wheels, this is wheel sets. So this is wheels, axles, and bearings. Bogies tend to be number 2. And then sort of everything else seems to be much further back in the list, except for the unknown or other. Again, looking at the EU study that was done a number of years ago, axles themselves are number 1. This includes, by the way, bearings. So this is not only axles, but this is also bearings. So what we call overheated bearings fall into this category as well. Wheels, bogies are the big 3. So axles and bearings, wheels, and bogies are the big 3.
Excuse me, DNV?
DNV was the name of the consulting company that did the study for the EU. So this was a European Union sponsored study of accidents.
Okay.
These results were found in that derail report that I mentioned earlier. And I actually gave you, let me see if I can go back to the derail report, because I believe I gave, hold on a second. Yeah, this report is actually available through the UIC website as well. And all of the DNV data came out of this report. Okay, we talked about this. If you look, okay, so in the DNV, axles and journals were number 1, bogies were number 2, wheels were number 3. If you look at the US one, wheels are number 1, again, because of a higher axle load. Bogies are number 2, axles and journals are number 3. Couplers and draft gear are number 4. Brakes are number 5. Car body is number 6. And again, I'm not going to spend a lot of detail on it. If you go internationally, interestingly enough, again, the US, you can see the wheels and the axles. Again, by German, in the European count, again, journals, axles and journal bearings are the big one in the European side. Oh, okay. The third area we're talking about is operations. And here to give you an idea of the range of type of problems associated with operations. So here we would have unfavorable train composition. What would happen on, for example, putting empties in front of loaded wagons? Numerous engineering studies have been found that basically says that if you make up a train and you put your empties behind your locomotive and then you put your loaded wagons behind the empties in a freight wagon, you're very likely to have an accident when you have a severe braking application, because what happens is all the loaded wagons run in, generate a large longitudinal force. If you're on a curve, that gives you a large lateral component, which gives you a large L over V, because your V is small because the ones in front are empty. So a high lateral force associated from a run-in. So if I'm on a curve and I have a bunch of empty wagons here, and then I have loaded wagons over here, and for example, I have to brake, then all of a sudden I develop a large longitudinal force, which has a lateral component. The vertical component is low because these are empties. So the L over V is high. And if everybody remembers what I taught them, over the summer, high L over V gives you a risk of wheel climb, which is what happens. And so that train composition, can be a serious cause for accidents, as is improper loading of wagons. For example, overloading or skew loading. Overloading, which I put too much weight in the wagon. Skew loading is a little bit more problem, where the wagon is unevenly loaded. So if I have a wagon, bogey here, bogey here, and if I put more of the weight here and less of the weight here, then I have a higher vertical load here and lower vertical load here. And so I have a non-uniform loading. So likewise, if I load it improperly from side to side, or if my loading shifts, all of these we see as serious causes for accidents. So these all fall into the category of operations accidents. Speed, obviously, braking, point switch to a new position while the point is occupied by a train. Wrong setting in a switch point. So this you can see is a big issue here. Particularly, we see this in yards, where the switch point is not, the switch is not set to the position in the right direction where you're going to go. And in fact, it's set where you have a vehicle operating. Overspeed I mentioned, brake problems, too high a speed through a turnout, human factors. Operator is falling asleep, operators using drugs, operators on using on the cell phone. All of those are human factor type operations. You can see in Great Britain, because of the way they look at their accidents, they have a very high preponderance of human factors one. The EU study, train loading, mishandling of train formation. So this is really the loading of the wagons. This is where you place the wagons, where you're putting your empty wagons in front of your loaded track wagons. You don't perform your train test, your brake tests, etc. This is where you have your turnouts, your switch points in the wrong position. This is the US. Again, improper use of switches in the wrong position, train handling and makeup, overspeed, etc. If we put them all together, in fact, let's skip these two and go here. Okay. So if we start looking at what are the major causes across the board, this is a combination of EU data and the EU DNV study data, where basically axle failures, wheel failures, and excessive track width were numbers 1, 2, and 3. Improper loading, excessive track twist. You can see track geometry is here, here, and here. So these are track geometry related. These are wheel and axle related. These are rail related. You can see rail ends up being in the top 10 as well, even under the lighter EU axle load type of behavior. Spring and suspension failure, etc. Okay. Again, if you when you look at the different, you look at the European derailment data, you'll see human factors, track geometry, rail failure, switches, switch in wrong position. So the difference between this, which is a switch structural failure, which is an infrastructure failure, and wrong setting of the switch, which is an operation.
Oh,
So let me make this point here for a moment. Okay. One of the issues that we run into when we talk about what are the worst type of derailments is, are we basing it based on numbers? Are we basing them based on cost? So this is the UIC data distribution based on numbers, as is this. This is the number of derailments. If we look at the UIC distribution based on costs, you'll see that they don't quite match. That the ones with the most number of accidents, like human factors, are not necessarily the most expensive ones. So if we look at the data this way, it maybe makes a little bit more sense. Here are the top 10 accident causes, this happens to be US data, based on number of accidents, total costs, costs per derailment, and derailments per year. Okay, so for example, if we look at derailments per year, we'll see number one, the one with the most derailments per year is basically switching operations. And number two is track geometry. And number three is broken rail. And then the next one, a distant number four, is improper use of switches and frogs and frog failure. But if we look at the cost per derailment, look at the total costs to start with, you can see rail defects generated cost. Track geometry defects represent the second most costs. Wheel failure represented number three. And wheel failure didn't even appear in the top five over here. If we look at the cost per accident or cost per derailment, we'll see that wheel failure was actually the most expensive one. Oop. Go back here. Sorry, axle bearing.
אנג'ליקה, שימי על מיוט, זה מפריע.
We are happy.
Okay, somebody needs to be on.
Oh, you did
Alan,
so
can you
good.
put everybody on mute?
Yes,
You did so good.
figure out how to do it here.
יש לי שלוש, יש לי שלוש. כן.
I'm trying to figure out how to mute everybody.
כל הכבוד לך, בגלל זה פה. Okay. You did so good. I'm so proud of you. רגע.
Ellen, she's on mute. You can go on.
Okay, I see a couple of people that weren't on mute, so I just changed it.
Thank you.
Okay. Hopefully everybody's on mute now. Okay, sorry. Okay, so let's take a step back. Okay. All right. So the point I want to make when I look at what's the worst cause of derailment is it's based on what's my criteria. If my criteria is total cost, how much the total cost of all the accidents to a railroad is going to be, then if I look at this data, it says rail is number one, track geometry is number two, wheel is number three, axles four, whatever. If I look at the number of accidents, then switching is number one, geometry is number two, rail is number three. If I look at the cost per derailment, then axles are number one, wheel is number two, and rail is number three. So when you talk about what's my major problem with derailments or accidents, it also depends on how you count it. If I'm looking at it from the point of view of where do I invest my greatest amount of money, one of the problems we run into is things like it's much more difficult to address an accident problem where I have 20 a year as opposed to 200 a year. Remember, this is US numbers. So we're dealing with a very large system. We're dealing with 300,000 kilometers of railroads and about 15 billion ton kilometers of traffic. No, 15 trillion ton kilometers of traffic. This is one of the reasons, one of the questions that get asked is, how come we don't do a better job of finding the accidents? Is one of the problems here. Let's, if we go back into a category, this is 10 years worth of data. So let's take improper use of switch here. That's about $4 million a year. If it's going to cost me $100 million to prevent those $4 million of accidents, I really got to think twice, unless I got deaths or fatalities involved in here, which for the most part I do not, because the improper use of switch, by the way, tends to be low speed accidents. You can see the cost per derailment is about $60,000. It's significantly down on the list here. So this is one of the issues we run into when we're dealing with accidents. The UIC Derail Committee, when they started going through all the studies that they went through, they basically listed axle rupture, including bearing failure and journal failure, to be the largest cause of accidents. Does everybody understand what a bearing and a journal is? Anybody not understand it?
No, I don't.
Okay, so when you have you have your wheel, right? And you have your axle connecting the wheel. You have a bearing that goes between the wheel and the axle. Let me see if I have a good picture of that. I have it in another presentation. Hold on a second. Let me find you that picture so I can show you that. Okay, so I have my can't see that. Huh? Okay, so I have my wheel, I have my axle, I have my other wheel. These are all rigidly connecting, they're rotating, right? But they have to be connected to the bogie. And so this is the side frame of the bogie. And at the end of the axle, I put a bearing. And then I drop my side frame with an adapter on top of my bearing. So what the bearing does is
Sorry, we cannot see the drawing.
I think you didn't share your picture.
Yes, please.
Sorry. Can you see it now?
Yes.
Okay. Do I have a picture? Okay. So if we look at a bogie, we have our two wheels, we have an axle, And then at the end of the axle, we have a bearing, as you can see over here. Now, the wheels rotate, obviously. The wheels and the axles are ridges, so they rotate together. Obviously, the side frame does not rotate. So the bearing, which is placed on the end of the axle, and then the side frame comes down on top of it, as you can see over here with an adapter. This allows the wheel axle set to rotate inside the bogie. This is called the bearing, and sometimes it's also referred to as the journal, because an older type of bearing used to be what's called the journal bearing, and the terminology still is existent today. So a lot of the railroads still refer to the bearing as a journal bearing. And we'll talk about bearings next week. Okay, why can't I get? 1 second. Can you see that? Can you see my screen now? Does everybody see my screen?
Yes.
Okay. All right. So failure of the axle to include overheating of that bearing. We're going to talk about that next week, actually. But overheating of the bearing has actually been identified by the UIC as being their top cause of accidents. Excessive track width, which includes wide gauge, is number 2. Wheel failure is number 3. Improper loading of the wagon is number 4. Excessive track twist, when the rail, when the cross level is first to one side and then to the other, so that you have a change in cross level over time. That's a twist. Oh, change in cross level over space, over distance. That's a twist. That's number 5. Track height or cant is number 6. Broken rail is number 7. And spring and suspension failure is number 8. And again, you've got various ones. Russian derailment causes, interestingly enough, failure of bogies seem to be number 1, and failure of the Russians seem to have a higher percentage of mechanical failures than either the Europeans or the Americans. The British, and I know the British is always of interest to Israel, because the Israel Railway was founded originally in the Rich one. You can see again 2 rankings, ranked by frequency and ranked by cost. So again, the British also recognize the fact that there's a difference between the most common accidents and the most expensive accidents. So from the frequency point of view, human factors, excessive twist, switch component failure, rolling stock, excessive track width, which is track geometry, other infrastructure failure, other operational failure, etc. On the most expensive side, spring and suspension, track geometry, other track geometry, excessive, failure to carry out work rules, which is human factors, and then rail and fastenings. When the British looked into track-related derailments, switches and crossings, gauge spread, track twist. I'm not going to go through every country. You can see France is very similar to the UIC type of numbers, with hot axle boxes and axle failures being number 1 and track geometry number 2, and wagon wrongly improperly loaded number 3, weather 4, rail 5. Okay. So for the next 15 minutes or so, I'm just going to quickly go through and just, I don't want you to memorize these, but I want to sort of give you an idea of, up until now, we're talking about broad categories. I want to go and I want to show you just how many different subcategories there are in an accident, which why getting rid of every accident is such a really difficult issue. So, and I'm going to use the FRA, the US data, just because they have a very nice method of identifying the accident causes that's intuitive. And so we're going to follow that. So on the major category side, so we talked about this, you have track-caused derailments, signal-caused derailments, equipment-caused derailments, train operation, humans factors, and miscellaneous. And miscellaneous includes things like weather, for example. And depending on you count, this tends to be number 1, this tends to be number 2, this tends to be number 3, this tends to be number 4, and this tends to be number 5. If I look at the track subcategory, the track category, I break that down into subcategories of rail, joint bar, and fastenings, track geometry, roadbed, switches, frogs, and turnouts, and then a general other miscellaneous category. If I then break that down further, if we go to track and roadbed, for example, or track geometry, you can see I have cross level at joints, cross level not at joints, deviation of profile, disturbed ballast section, insufficient ballast section, super elevation. You notice I have 14 different categories here. Why? I have 4 different types of Y gauge, all due to different reasons. Y gauge due to missing sleepers, Y gauge due to missing fasteners, Y gauge due to defective gauge rides, Y gauge due to worn rail. I have improper elevation or cant. I have improper track alignment. And I also have a buckle track, which is separate than the track day alignment. So again, you can get a flavor for the type of defects you have. If I look at broken rail, I have about 25 different categories of rail breaks, including bolt holes, plant welds, field welds, head and web separations, engine burn fractures, detail fracture from a shell, pipe rail. All of these we've discussed in detail, so you should be familiar with. But again, each one of these is a slightly different category. And a broken rail is not a broken rail is not a broken rail. A broken rail due to a detail fracture from a shell is very different than a broken rail due to a bolt hole crack or a broken rail due to a defective field weld. Very, very different types of failure mechanisms. Again, frogs and switches. There are about 20 different subcategories, and I'm not going to go into them. I just want to familiarize you with them. Signal and communications. Again, you can get a flavor for the different types of factors that we're looking at here. Mechanical, We sort of went through this briefly: wheels, axles, and bearings, bogie components, couplers, car body. We'll talk about car body a little bit. Car body is a very important subcategory because it often affects how many people get killed in an accident. Trailer, container on flat car, improper brakes, locomotives, doors, etc. And again, each of these, and I'm not going to go into it, but again, give you an idea. Each of these axles and German bearings, here we have what? We have 18 different categories. Human factors, use of the brakes, as opposed to when we talked about brakes here, we talked about a failure in the brake mechanism. When we talk about human factors, we're talking about the train driver not properly using the brakes or not properly setting the brakes. And we'll give you some examples of that, some really nasty examples of that when we get to that in 2 weeks. Employee physical condition, drug and alcohol, sleep apnea. These days, being distracted by a cell phone falls into that category. Switching rules, train handling, how you handle the train, how you make up the train, overspeed. Again, major subcategories. Again, look at train handling. I have 25 subcategories of train handling, which I'm not going to go into the discussion here. Miscellaneous, environmental conditions, certain types of grade crossings, improper loading, depending on how it's defined. This is the most common one: weather, environmental conditions, flooding, snow, high winds, etc. Okay, so after going through all these causes, the feeling is that most of the time a derailment has a single or dominant cause. And that's true roughly 75% of the time. About 75% of the derailments have a single dominant cause. The problem is the other 25% of the derailments have multiple causes. So what's a multiple cause derailment? A multiple cause derailment or a multiple cause accident is an accident with more than one cause. That if you have, for example, 2 or 3 causes and you eliminate one of them, or you have 2 or 3 contributing factors, then you eliminate one of them, the accident probably wouldn't have happened. But since most railroads require you to pick a cause, usually you end up picking the more dominant cause. But for those 25% of the accidents, there are multiple causes, and the multiple causes almost always very, very commonly include track geometry, improper loading, mishandling, something wrong with the wheel. My most common, my favorite example, and I don't remember if I gave it to you or not, is when I was investigating a derailment in BART, the BART Metro, the San Francisco Metro System, BART, about 20 years ago. It was a wheel climb derailment where the wheel basically climbed the rail, and this was in a subway underground. So the wagon, the passenger wagon smashed against the side of the tunnel and tore up the side of the wagon and sent people to the hospital and all good stuff like that. when I had a meeting with the different groups, and of course we had the track people and we had the equipment people and we had the operating people. The track people said, this derailment is not our cause, we were within standards. And the equipment people said, this derailment is not within cause, we were within standards. And the operating stats people said, this derailment is not our fault, we were within operating rules and we were within proper speed limits. And that was an example where there was a overlap. There was no clear track geometry problem, or there was no clear wheel and rail problem, and there was no clear overspeed problem. But it turned out the wheel was worn close to the limit, and the rail was worn close to the limit, and the speed was right at the limit. And that combination caused that derailment. And that's a sort of a typical, that's an example of an accident with multiple causes and all. And as we go through this process, I'll give you specific examples later on. So just real quickly, just to refresh your memory or to show you that, let me sort of give you an idea what some of these things look like. And I'm going to go into this a little bit more detail in the next couple of weeks. So rail failure, you all recall, one of the most common types of rail failure is a detail fracture from shell, often associating with rolling contact fatigue, which is a form of micro cracking in the gauge cohesion of the rail. That micro cracking can develop into a transverse defect and the rail will fracture. And this is a detail fracture from a shell. Okay, these are transverse defects from an inclusion. So if you look inside, you see there's some sort of initiation point. In these particular cases, there's probably some sort of hydrogen flake or some sort of impurity in the manufacturing, and the defect will develop from here. So this is a transverse defect. This is our friend rail corrugations, which we spent a lot of time talking about. Again, different types of rail failure we're going to go through. And this is the growth of a detail fracture from a shell transversely until it fractures. Oh boy. Somebody's dropped something there. Okay, I just muted everybody. I just figured out how to do this again. All right. Okay, broken rail. Now it's interesting. Broken rail, I just 2 years ago, I investigated a broken rail derailment in Washington Metro. Again, a metro. So those of you who are in the metro business who say rail problems are not an issue, we can get away with a small rail section and we don't really have to worry about the rail because they don't break very much. The answer is they do break. The broken rail defect that I investigated in Washington Metro, it turned out there was a corrosion. There was corrosion on the base, on the bottom of the rail, on the underside of the rail, because this was in a wet tunnel. And the corrosion served as a defect initiator. And in fact, what happened in that particular, this picture was not from this, it was from a different one. But what happened there is the defect grew up and actually did what shows over here, turned sideways and then came back up. So it came up, it came up, sideways, and then went back up. And it initiated from a stress concentration due to corrosion on the base, on the underside of the rail. So it was even basically non-detectable. Pull apart, you remember high thermal forces associated with temperature change. which we have, if you lay it very hot, which is the Israeli practice, and you get a really cold spell, then you can develop very high tensile stresses in the rail, and you can literally shear off the bolts. You can see there are no bolts on this side of the joint bar. They were sheared off, so this rail opens up. And it can open up quite significantly, as you can see over here. Defective thermit weld. Improper weld. Lack of fusion. Source of failure. Joint failure. High dynamic loads can result in fracture of the joint of the bolt, and you can have very significant surface defects that generate very high wheel impact loads. These types of wheel impact loads can generate factors of 4. So if you have a UIC freight wagon with a 22 ton axle load, 22 and a half ton axle load. So the wheel load is what, 11.25 tons. Underneath this or underneath that, that can be close to 45 tons dynamic load right at that one spot, which can cause fracture of just about anything. Track geometry, you can see that pretty nasty low spot there, but here you can see the twist, okay? You can see I'm low to this side, and then I'm low to this side. So I'm going down here, and then I'm reversing it down here, and I'm gonna actually have my vehicle rocking back and forth. Remember the rock and roll we talked about before. Again, cross level, twist, surface profile. Another example of track geometry for surface. Poor alignment. Alignment is lateral track geometry. All of these can generate excessive dynamic response. You can have your rocking, which you can see over here. You can have your pitch and bounce, which you can see over here. So if you follow the UIC practice of having your welds opposite each other and they both batter down and they start getting battered welds, you can get this type of pitch and bounce type of dynamic behavior. We talked about that in the previous class. Excessive track width, wide gauge, of course. Wheel failure, we're going to talk about that next week. But we can have wheel is almost a first cousin of the rail. So all of the problems we've talked about in the rail, rolling contact fatigue, surface spalling, shelling, internal fracture, all of these develop in the wheel. And we'll talk about that in detail next week. You can see cracked, plus you can see shelling of the tread, plus you can have things like loose wheels. Washington Metro, again, I'm pointing out metros because very often I hear from people who are associated with metros that they don't really worry about these things because they don't happen very often. You're right, they don't happen very often, but when they happen, they're a real problem. Okay, Washington Metro just had a derailment associated with improper back-to-back wheel spacing. So the spacing, the back-to-back wheel spacing on the Metro car was, as I recall, was excessive. And the vehicle derailed. And they basically, because of that problem, they pulled that whole series of wagons out of service. which represented about 40% of the fleet. So they pulled 40% of the fleet out of the service to inspect the wheels. And because of the problems they found, movement of the wheel set, improper initial adjustment, that they actually haven't, to this day, they haven't returned all the wagons to service. They're still trying to figure out a way to get all the wagons back into service, which would be a major cause of service disruption. Washington Metro at the moment doesn't have enough wagons to operate the Metro at full capacity. They're operating at reduced capacity because of this back-to-back problem. Wear. Not only do you have wear and wear for angle, which we'll talk about because you all remember the Nadal limit, you can also have plastic flow, and you have this very thin high flange, which can basically slip between a switch point and a stock rail and cause a derailment. We'll talk about that next week as well. Slid flats, high dynamic impact generators. I did have a picture of a wheel axle and bearing here. Here we got a big picture. Here you got a wheel axle bearing and disc brake, by the way, here. So overheating bearings, major, as you saw from our previous discussion, a major cause of disruption. Now, this is obviously a broken wheel. Can't get more broken than that. Axle failure. This can be a fatigue initiator. And as I'll show you next week, you can actually have fatigue failure in your axle as well. Bearing failure. The most common mode of bearing failure, which we'll talk about next week, is overheating of the bearings. Remember, this is the #1 cause in the UIC listing. So this is a serious issue and one that you need to be aware of. And particularly, how do you detect it and how do you deal with it? We'll talk about that next week as well. Overheated, this is what happens when you have an overheated bearing. That bearing completely burned off. It went right through the axle. Remember, the bearing sits on the end of the axle. It overheated that, it burned off the end of the axle. And so the axle fell apart from the bogie because there was nothing supporting it. Special track work. We're going to devote an entire lecture to special track work and special track work related problems. See that switch point over there? Or you see that switch point is not over there? If you look down here, you see the switch point should have gone to the end, but you see it's broken off. So you can see these are real things. We find them in the real world. Frog batter, wing rail batter. This is all part of the frog problem. We'll talk about this inspection technology, but you can clearly see the batter over here. That's this wing rail batter right over there. Missing or broken bolts in the switch. We're going to talk about 2 major recent UK accidents, both of which killed people, associated with missing or broken bolts in the switch. You'd think the inspectors would find them, right? Well, we're going to talk about that. That will be a later lecture. Train handling. Train handling forces. Buff forces is compression. Draft forces is tension. I'm going up and down a grade. Going up in grade, my train is spread out. I have tensile forces going through my train. Going down the grade and braking, I have compressive forces. So my draft forces are here and my buff forces are here. Going around a curve, those forces translate into lateral forces in the coupler or in the connector. So if you have a hook and buff connector, those things don't handle lateral forces well at all. Improper or eccentric loading, you saw that among the list. So that can be front to back improper loading or side to side improper loading. Does this happen? You saw from the UIC statistics. This is one of their top 10 categories of accident causes. So this is a real cause in the UIC world. Improper switching, where the switch is improperly set. I'll show you a video. If we have time, I'll show it to you today. If not, I'll show it to you when we get to that lecture on human factors. Track buckle, we talked about a track buckle. Roadbed defects, mud, drainage. Yes, that's water sitting in there. Overspeed. This is one of the areas where positive train control or European train control systems are in fact controlling the speed better. Spring and suspension failure. Remember, that was #1 category in the Russian railroad world. So let's stop here, take our second break, come back at 10 to 12, and then we're going to get into really accident investigation and a case study, which I think you'll find a little bit less boring than just studying the statistics. But I want you to start keeping in mind those statistics because we're going to start talking about them as we go along. So let's take our break.